So welcome to the lecture. We will now start a discussion about Lorentz covariant generalization of Newton's theory of gravity. So we have seen that purely starting from electrostatic, if we impose certain condition or restriction, then we can end up with the correct Lorentz covariant generalization of it. That is the Maxwell's equation. We will now mimic those steps for Newton's theory of gravity, and let's see what happens. We will see that indeed, it is possible to have a Lorentz covariant generalization of Newton's theory of gravity at the linear level of field angles. So let's start doing that. So we will start with the Poincare equation satisfied by the Newtonian potential, which we denote by this symbol, capital phi subscript n, and del square phi n is 4 pi g Newton. Let's go. Now, to come up with the Lorentz covariant version of this equation, first take a look at the right hand side of this equation. So, in the context of electrostatic, we have the charge density as a source, and we know that together with the charge current, they form a 4 vector. So we have replaced the right hand side of the Poincare equation that we encountered in electrostatic by the charge current density 4 vector J mu, which has one Lorentz index. But remember that for the case of gravity, this rho is mass density, and from special relativity we know that there exists a mass energy equivalence, which tells us that rho times c square is equal to the energy density. And remember our discussion about stress energy momentum tensor in earlier lectures. So we have identified that the 0,0 component of the stress energy momentum tensor is proportional to the energy density. To be more precise, T00 is equal to epsilon by C. Remember our discussion in the context of fluid dynamics, where we have discussed the physical meaning of the 0,0 component of the stress energy momentum tensor, which is nothing by energy density divided by this. Then it is easy to guess that if we have to make this equation Lorentz covariant, then right hand side now has to be replaced by this stress energy momentum tensor. And unlike the electrodynamic, where the source is J mu, which have single Lorentz indices, now we'll have source as stress energy momentum tensor, which will have 2 Lorentz indices. So right hand side should be proportional to T mu, and this T mu now will generate the corresponding field, which we denote by capital phi mu. So before proceeding further, we will assume one fact from field theory, that if you have rotational and translational symmetry, then you can always make this stress tensor symmetric. That means the component of which will satisfy this condition. And our source will be a 2 rank tensor, which is conserved as well as symmetry in the 2 Lorentz indices. Then we can expect that the field that will be generated by it should also have the same property. So it will have two Lorentz index and symmetric in those two Lorentz index component of the field, right, which we denoted by capital phi. Okay. Now, right hand side will be, as discussed, proportional to T mu nu. Kappa bar is some proportionality constant that we will fix later on by taking suitable non-relativistic limit. At this point, kappa bar is some undetermined constant. And now, what about the left hand side of this equation? Again, this point the equation tells us that left hand side should contain at most two derivatives. We need only a second order equation, and also it should be linear in field, that is linear in capital phi. So schematically, it should be some function of two derivative, not writing the indices explicitly, and two derivative with some index here, index, two index of phi of this form. Some function of phi which is should be linear in phi and contain two there. So now remember that in this case, each of these derivatives will bring one Lorentz indices, and capital phi will have two Lorentz indices. But this side cannot have more than two free Lorentz indices, because right hand side have T mu nu, which has only two free Lorentz indices. So this four Lorentz indices, out of we have to pick two and contract them so that the remaining two will be free. Right? Otherwise, the left hand side and right hand side will not have the same nature under the Lorentz transform. And also, after contracting two out of the four Lorentz indices, it should be symmetric under the exchange of remaining two free Lorentz indices. Right? Remember, because if T mu nu can always be made symmetric, then phi mu nu, which is a canonical pair of T mu nu, remember our discussion of a canonical pair. So if you write down an action, we can contract this field and the source together to form a Lorentz scalar. So if T mu nu is symmetric, and it is sufficient that phi mu nu to be symmetric, because even if phi mu nu has an antisymmetric part, when you contract with phi mu nu with T mu nu, the antisymmetric part will not play any role. So we can actually assume that phi mu nu to be automatically symmetric. You will see more naturally that why this will be symmetric in the two Lorentz index in a later lecture. So now we have to write down the all possible term here for this function f, and there are quite a bit of them. So let's list them down. What are the possible terms, keeping this in mind that it should contain at most two derivatives. It will be symmetric under the exchange of the two free indices and linear in phi. Okay. So before proceeding further, one thing remember that at this point we are not claiming that the 0 index 0 component of this capital phi is equal to the Newtonian potential. Of course, they will be related with each other. That means capital phi 0 will be related to the Newtonian potential, but up to some linear transform. We are not unambiguously at this point identifying the 0 component of it with the Newtonian potential. And we will take advantage of this ambiguity to fix this form of this equation. We will see shortly. So let's now try to list down all possible terms for the right hand side of this equation. F will be a linear combination of these functions. A1 some arbitrary coefficient. This is again the D-Alam version. Then we can have A2 times del mu capital phi. And what is this capital phi? Capital phi is the trace of the phi mu field. Okay. Then we can have A3 multiplied two combination from del mu lambda, and this lambda will be contracted with one of the index mu, and of course we can interchange mu and mu, another possibility. This is, then we can also have A4 times eta mu box of phi. Remember, Minkowski metric is also symmetric in mu. So this term is also comparable with the right hand side in terms of symmetry. And we can have this term, coefficient times eta mu and two derivative sigma with contracted with this. Okay. And finally we have two more terms which will not include any derivative, just dependent on this field. 6, 7 eta mu, and this is equal to kappa bar T mu. Both side free indices are written in downstairs. You can raise and lower them by metric tensor, but for convenience, written in, we have put the free indices in the downstairs. Okay. Now we have A2 to A7, these coefficients, and kappa bar are determined coefficient. We have to determine. Again, we will impose some physical condition. Actually, we will mimic the steps that we have done for the electrodynamics. And let's see whether we can fix this coefficient and what is the resulting equation. First, remember that in the context of electrodynamics, if we have a term in the right hand side which do not contain any derivative, that is just proportional to the Maxwell gauge potential, that generates some kind of a mass term. And in the static limit, when we solve for the potential, it gives either a exponentially damped solution or sinusoidal solution depending on the sign of its coefficient. But we know that for Coulomb law, those kind of solution for a point charge does not exist. Similar thing happens that we don't want those kind of a damped or oscillating solution for a point mass. And if we keep these two terms, we will indeed get those kind of solution instead of just 1 over r type of potential, which is expected from Newton's law of gravity that we discussed. And also, you should be quite familiar with. So, in sense of this exponentially damped or the oscillatory solution makes this coefficient A6 and A7 0. A6, A7, so 0. Oscillatory. static point. So we can get rid of these two coefficients, but we still have this A1 to A5 and this kappa. Now we have used the Lorentz covariance to write this general form up to two derivative order linear in field phi and source t mu nu. And then we also imposed this absence of this exponentially damped oscillatory solution to get rid of these two coefficients. And next we impose that the t mu nu, the trace energy momentum tensor, should be constant. Del mu nu, t mu nu is equal to 0. And this gives the following. 1 plus A3 box of mu plus A2 plus A4 del mu box 5 plus A3 plus A5 del mu is equal to 0. So you can take this equation, of course this is set to 0, and act both sides by a del mu, and you will get what I have written. So this is a very simple exercise. You should do it explicitly. Now these three are three different independent tensor structure. So if total thing has to be 0, then coefficient of each of them has to be separately set to 0. This gives A1 plus A3 equal to 0, A2 plus A4 equal to 0, and A3 plus A5 equal to 0. So now you can see from here, you can determine two of the coefficients, right? Let's say we replace A3 and A4 by this first two equation in terms of A1, A2, and of course A3 and A4 will again related, A5 will be related to each other. So effectively, we can get rid of the three coefficients using these three equations. So then we get the following. We have A1 box of capital phi mu nu plus A2 del nu the 5, which is the trace capital phi, A1 del mu del lambda capital phi del lambda mu plus del lambda del nu. These two terms is basically found by interchanging mu indices, and then we have A2 times eta mu nu box of phi plus A1 eta mu nu del rho del sigma. So sigma is equal to some bar T. Now let's divide both sides by A1. A1, and we get box capital phi mu nu minus, so this A1 will not be there, mu del lambda capital phi plus del nu right. And then we have eta, this term plus eta mu nu rho sigma. Okay. Remember phi symmetric under the extent of 2 index. So phi lambda mu is equal to phi mu lambda. And then we call, when we divide by A1, so A2 by A1, we call it just A. So we have A by del nu minus mu nu box of phi equal to, and we call kappa bar by A1 as some kappa in, or A is basically A2 by A1 and kappa is A. But it doesn't matter. Effectively now we have to fix two undetermined constants. But now, if you think carefully, we have already exhausted whatever we did for electrodynamics. So we have used Lorentz covariance. We have used the fact that there is no oscillatory or damped solution in the static limit for a point particle potential. It should go as 1 over r. We also use the conservation of trace energy momentum tensor. But still, we are left with two undetermined constants. Remember for the electrodynamics, we are left with just one constant which we fix by taking the non-relativistic limit and then identifying the potential with the corresponding electrostatic potential, and that fixes the last constant. But we will do that. We will take the non-relativistic limit of the equation, but still, in this case, we have not just one constant, but two arbitrary constants. So what we should do? Actually, there is one more thing that we can do here is the following. Remember that we haven't identified capital phi mu nu unambiguously, or rather the 0,0 component of it unambiguously with that of the Newtonian potential phi of it. They are related, but they can be related up to some linear transform. And that gives us a way to fix one of these undetermined constants. This is something we call in physics is field redefinition. Okay. So let's introduce another field, H mu nu, which is related to pi mu nu plus some undetermined constant B, which we can choose freely, times eta mu nu. So H is related to phi linearly, and H mu nu also symmetric under the interchange of mu nu index. Thus phi is symmetric, eta is symmetric. Now we can rewrite this equation in terms of this redefined field, H mu. This is we called field redefinition. So if you rewrite this in terms of H mu nu, then basically you get a similar looking equation. But still, again, let's write it down explicitly. We have box H mu nu minus del mu del lambda nu plus del lambda del nu mu lambda eta mu nu del rho del sigma h rho sigma plus now we have a new constant which we write a bar instead of a del nu del eta mu nu box acting on the h. H is the trace of h mu. Right. H is eta mu nu trace equal to kappa t mu nu. So this equation is again of same form as that of this equation written in terms of phi. Kindly check that indeed you get this actually by explicitly putting h instead of phi in this equation and derive the equation for h. We leave that as an exercise for it. But now this constant has been changed. Instead of a, we have now a bar, and this a bar is defined as a plus 2b by 1 plus d times b. And d is the space-time dimension. So note that all our arguments are fairly generic. So we are not particularly restricting ourselves to 3 plus 1 dimension. You can just put that in d equal to 4, but we will keep it as a general dimension. And d is nothing but eta mu nu and eta mu nu. You can check that this will give the trace of eta. So in d dimension, it will have d entries. So trace will be some of them, but minus will multiply with a minus because of the it is eta inverse and eta both has the first entry minus. So it will have a sum over d number of 1. So it meets the space-time dimension d. So now inside A, you can see we have this A, the previously undetermined constant, and now this B. B, because of field redefinition, we can choose B anything we want. In fact, now we are going to use this freedom of field redefinition to adjust B such that we can fix this A bar. So we can, in fact, we can choose B such that this A bar goes to 0 even. So if you put B equal to minus A by 2, A bar is 0 basically. But we will not going to make that particular choice. You can, but we will not going to make that choice. The reason will be clear in the later part of the course, especially when we discuss this gravitational wave equation. We'll see. So we will choose instead the B such that A bar becomes 1. You can see that there is always exists a choice for me. So now we have got rid of this undetermined constant as well, and we get the following box of h mu nu minus del mu lambda nu plus del nu lambda and lambda plus del nu h plus eta mu nu del sigma minus box of h equal to kappa t mu. And this equation is known as the Pauli-Fierz equation. Or Fierz-Pauli equation. whichever way you want. So the relativistic generalization of the Newton's law of gravity at the linear level of the gravitational field gives you the Fierz-Pauli equation. And this tensorial gravitational potential field H mu nu is known as the Fierz-Pauli field. This is nothing but a linearized gravitational field whose equation of motion is second order. And of course, it is linear in H mu as well as the source. So in and you will also encounter this in quantum field theory literature as a linearized gravitational field. And if you quantize this field, we'll have the spin 2 graviton. So note that we still have to determine the kappa, which we'll do by taking the non-relativistic limit and identifying the H00 component with the Newtonian potential, which we'll do in the next lecture. So, thank you for listening. We will end.